Class 11th, Subject Physics, 3rd chapter, Motion in a Plane. From the chapter, let us see average and instantaneous acceleration for the motion in a plane, that is motion of the particle in 2 dimensions. So in case of rectilinear motion and the motion in a plane, the acceleration will be defined in the similar way, and therefore acceleration is defined as the rate of change of velocity with respect to time, that is change in velocity upon time. But in case of motion in a plane, we will consider the velocities in vector form, and therefore let vector v1 given as in terms of its x and y components as v1x I cap plus v1y j cap be the velocity of the particle at time t1, and let vector v2 in terms of its x and y components given as v2x I cap plus v2y j cap be the velocity of the particle at time t2, and therefore from v1 and v2 we can write the expression for average acceleration for sufficiently large time interval, that is vector AV, that is the average acceleration of the particle between time t1 and t2. So if this time interval between t1 and t2 is sufficiently large, then we can define the average acceleration, which is given as average acceleration vector AV, that is equal to change in velocity upon change in time, that is vector v2 minus vector v1 upon t2 minus t1. So putting the values of v2 and v1 here, we can write v2x I cap plus v2y j cap minus v1x I cap plus v1y j cap and divided by time interval t2 minus t1. Then for the next step, we will combine the terms of I cap and j cap and j cap, and therefore we can write average acceleration, that is vector AV, will be equal to v2x minus v1x upon t2 minus t1 I cap. This denominator will be separated for I and j terms, and therefore we can write v2x minus v1x upon t2 minus t1 I cap, that is v2x minus v1x divided by t2 minus t1 I cap plus v2y minus v1y upon t2 minus t1 j cap. That will be written as AAV x I cap plus AAV y j cap as equation number 1, where these two terms written in equation 1, that is AAVx and AAVy, are x and y components. These two terms are x and y components of the average acceleration. So this is the x component, this is the y component of average acceleration, and therefore the magnitude and direction of this average acceleration will be given in terms of x and y components of the average acceleration, and therefore the magnitude and direction of the average acceleration are given as, this is the magnitude of average acceleration, that is AAV, will be equal to square root of A average x square plus A average y square So this equation will represent the magnitude of average acceleration. Then its direction will be given in terms of tangent of angle theta, that is tan theta is equal to AAVy, that is y component, divided by AAVx, that is x component, equation number 2. So equation number 2 will give us the magnitude as well as direction of the average acceleration. Now, if the time interval between t1 and t2 is infinitesimal, that is very small interval of time, if that time interval t is tending to 0, then we can define the instantaneous acceleration, and therefore the instantaneous acceleration of that particle will be given as instantaneous acceleration vector A equal to, here limit t tends to 0, that is time interval will be tending to 0, delta V upon delta t. This will be written in the form of derivative of velocity, that is dv by dt. Now it will be written in terms of the unit vectors I and j as dvx by dt I cap plus dvy by dt j cap. So this dv by dt will be written in the form of vectors I cap and j cap as it is. Then further this will be written as velocity is the rate of change of displacement with respect to time, that is dx by dt. Therefore we can write acceleration A equal to d by dt of dx by dt I cap d by dt, that is derivative of this velocity, that is dx by dt I cap plus d by dt of dy by dt j cap. So in terms of displacement, that velocity is expressed. Now this will represent the double derivative, this will also represent double derivative, and therefore it will be written as d square x by dt square I cap, d square x by dt square I cap plus d square y by dt square j cap, equation number 3. So this equation number 3 will represent the instantaneous acceleration of that particle. Therefore, x and y components of the instantaneous acceleration will be given as the x and y components of the instantaneous acceleration, that is ax equal to d square x by dt square, ax equal to d square x by dt square, this will be the x component, and ay equal to d square y by dt square, this will represent the y component. Now in terms of this x and y components, now we can write the magnitude and direction of the instantaneous acceleration. So the magnitude and direction of the instantaneous acceleration are given in terms of x and y components as a is equal to square root of d square x by dt square whole square plus d square y by dt square whole square. So this equation will represent the magnitude of instantaneous acceleration, and its direction will be given as tan of angle theta, that is tan theta equal to dvy by dt divided by dvx by dt. Now this will be further written as this dvy by dt as it is dvy by dt and into dt upon dvx. This will be inverted, so it will be into dt upon dvx. dt will get cancelled and we will get dvy upon dvx only, and therefore we can write tan theta equal to dvy upon dvx, equation number 4. So this equation 4, this total, that is magnitude as well as this direction, is represented by equation 4, and therefore from this equation 4 this tan theta equal to d phi y upon d phi x represents, so it is the slope of the tangent to the curve in velocity graph. If we plot the velocity graph, then this tan theta is equal to d phi y by dx will represent the slope of the tangent to that curve of the velocity graph, that is the graph of phi y against phi x. If we plot the graph of phi y against phi x, then the slope of the tangent to that curve in velocity graph will represent the direction of instantaneous acceleration.